Welcome everyone to the second talk of this course. Second talk. So in the first talk, we learned about what is differentiation in Rn to Rn in terms of linear transformation. I mean, if there is a linear transformation lambda from Rn to Rn such that f a plus h minus f a minus lambda h, this norm by this norm limit h tends to 0 is 0. Then f is said to be differentiable at the point alpha. Differentiable at a. But finding this type of linear transformation or guessing sometimes may be tricky. So we will learn, okay, how to do this. Actually, this is component-wise the differential function. Okay, so now in this today's talk, I will mainly emphasize on chain rule and properties of differential functions. So mostly I will try to finish the chain rule by today, and if possible, if time permits, I will also try to explain you the properties of differential functions here. So before starting, I will first try to start with the talk with the help of a lemma, and I will use it. What does the lemma say? The lemma says that T Rn to Rn be a linear transformation in there exists a number or constant m such that this E of h, this will be less than m into this. I will use this, okay, in the chain rule. So observe this. This again I am saying it is norm actually. This is taken in Rm. This norm of Rm and this is norm of Rn. Actually, you can think that as a modulus, okay. For now, for instance, you can think this is that as a modulus. So okay. Same age, okay. H belongs to Rn. You can think that as a modulus, for instance. So now after taking modulus, I am in R. So this number is from R. This number is from R, and also M is an ideal number. Okay. I mean M belongs to R, so I can compare them. So I need to put this first. So net age belongs to Rm. Then what is TH? TH is nothing but the basis, the scalar combination, R linear combinations of elementary vectors of Rm. So I can write Tm as Rn to Rm. Okay. Rm to R. So okay, for Rm, because that was not matching then. Okay. So TH will be, suppose, alpha 1 or E1 plus alpha 2e2 plus alpha n en. Because this forms a basis e1 where ei 0 0. This is the right position. So it is TH. I mean where one occurs only at right position and except around 0. Then what is T of H? Okay, so let H be this thing first. Let H be this thing. So it is Rm. So it will be coming from Rm. Then T of H is nothing but T of this thing. Okay. But T is a linear transformation. So this is exactly equal to this of linear. So scalar will come out alpha 1 of E1 plus dot 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 plus alpha n. Okay. Now I can use the triangle inequality to conclude that so I can obviously use the triangle inequality to obtain that. That is nothing but alpha 1 t e1 plus modulus of alpha m. Okay. Now what I will do, I will do one thing here. Now observe one thing. What to observe? Now observe one thing. Each take any alpha I. Okay. So that is equals to alpha 1 square dot 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 plus alpha I square plus dot 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 plus alpha m square. But that is the norm of A. So each alpha I being less than equals to norm of H. Therefore, this is less equals to norm of H. Okay. And take, we will take m dash equal to max of PEI where 1 less I less m. Then we get okay. So let me clear a thing that I am taking norm of AI. Then why I am calculating one only in modulus? You might be wondering because there is a result in functional analysis. Any finite dimensional vector space, Rn is even Rn is even more real. It is complete. So in a finite dimensional vector space, any two norms are equivalent. So I don't make so starting with an unknown norm, I can also work with modulus because modulus gives a norm, modulus value. So take m dash. So what we get from here? What we get from here? We get norm of pH is less equals to m dash. There are m terms, so there will be m if I am not mistaken. Now take m equal to m dash everywhere. Then you get okay. So our lemma is proof. We will use it. We will use it to prove the chain rule. So let me remember for an instance what is the chain rule first. So chain rule means suppose for example in one variable derivative or one variable calculus, you know what is dds. So what we do, we did 2 is there sin x, then sin x, d of dx of sin x. Okay, that means in general two differentiable functions are there. Okay, f and g. So if we want to do derivative with respect to one thing, suppose dx of sin x were here, but we can uh, do this thing, I mean, even better. Sorry. For example, yeah, what is this thing? I was just sorry for the explanation. Sorry, what is this? So this is sine theta, sine applied on x square. So this is composition of two, derivative of composition of two functions, right? One is x square, then you apply sine theta on it. Then the mixed derivative you need to find out. So it is the derivative of the composition. So what we do in this case? In this case, we will first do that. First, do the derivative of that composite function with respect to a suitable variable. Then finally, derivative the suitable variable with respect to the initial variable. That is the chain rule, right? So if there is G compose F, what is this? They are both derivable, okay? Derivative exists at every point, or take the point on which, or the domain on which the derivative is defined. So if we do this, this is nothing but this is G dash of fx into f dash x. So we will develop these things in calculus of Rn. We will develop a similar argument like this. So theorem, chain rule of derivative. Let f first function is suppose Rn to Rn and be a differentiable function. The differentiable at A belongs to Rn and let G be another function from Rm to some Rp. If A obviously belongs to Rm, then the composite function. What is the composite function here? The composite function is G compose F, which is defined directly from Rn to Rp. Is differentiable. So why it will be differentiable? Because it will take the value A. So it is differentiable at A, not Fa. At the point A. Moreover, precisely, this is the main chain rule. What is the derivative of the composite function? D of G compose F at A equal to what is D of, G compose F means G of Fa. So first do G with G of F and evaluate that, and then F dash. Evaluate that at A and separately evaluate F dash and multiply them. So there is some picture. Suppose it is Rn, Rm, Rp. A is a point. I apply F and I get Fa. I apply G. What I will get? G compose Fa or G of Fa. Also, in this way, I can also visit the composite function. Obviously, it is G of Fa. Oh, G of Fa. And they are equal, right? They are equal. So the derivative of the composite function is this. So remember, D of Fa is a linear operator. Sometimes it is written as this. Because D of Fa was someone, it is lambda. So it is a linear operator. So I think this thing is clear. The statement is clear to you. Now I would proceed how to put the proof. The proof. So our proof is motivated by SpyHacks calculus on the book's title is Calculus on Manifolds. So we will try to do our proof according to SpyHacks book. So let us introduce some notation. Let us assume let if A equal to B, that means that element is B, lambda let lambda be the linear operator or the linear map. What is the linear map? d of fa, and mu be the linear map d of g of f of x. This is we assumed, right? So in the previous lecture, we sometimes denoted lambda by d of f at a. So d of f of a, it is applied on h, that is lambda of h. That is the value. And mu is the linear map, this d of g of a. So it is a first lambda is defined from this, and mu is defined from this here, d of g of f. Here you can see. So let us define. We will define some notations here, or for the simplicity of the proof. First is phi x. What is phi x? Phi x is fx minus fa minus lambda into x minus a. Lambda is a linear transformation, so the value of lambda at x minus a. 2 psi of y is g of y minus g of b minus mu of y minus. And lastly, rho x. What is rho? Rho is the same thing on the composition. Okay, that means g compose fx. That is g compose f applied on x minus g compose f applied on y a minus mu compose lambda applied on x minus a. So okay, now you might check the domains are same, codomains are same. G compose f will lie in Rp. Okay, and mu lambda is a linear transformation from Rn to Rm. When we compose this, so this is a value in Rm, and this is again a linear transformation from Rm to Rp. This is a linear transformation for, so they will lie in Rp, and these things always lie in Rp. So the same things, the codomains are defined. Check the codomains each map same. I mean codomain, so I can talk about plus and minus. Then we have what we have. Okay. Note that psi x by x minus alpha. Okay. X minus alpha is what? It is fx minus f minus alpha minus lambda of x minus alpha by x minus a. Okay. This is now sometime I say that same thing, right? X equal to c, if you assume x equal to a plus h, then this is something like f of a plus h minus f a minus lambda h by h. This is the same notation, okay? So what is the, I mean the limit where x tends to a, psi x by x minus a. What is the limit? So this is fine, right? This is differentiable, and so this is the correct linear map here. So this is 0. This we assume that as 4. Similarly what? Similarly, what is phi y by y minus b? This is same thing as gy minus gb minus lambda of, sorry, it is mu, so it will be mu evaluated at y minus b by y minus b. Similarly, this implies that this modulus limit y tends to b, sorry, this is psi y divided by y minus b. This is also 0. So we name this is as 5. Okay. So everything is going fine till now. Now observe one thing, that for this we have this, for these things we have this. Now we want to prove that for this thing. So if we show this analogous formula for this thing, that is the composition thing, then we are done. Then we are done. So I want to show that analogous formula for rho x holds. That means limit x tends to a modulus of rho x or norm of rho x divided by x minus alpha equal to 0. Now why I want to show this? Why I want to show this? I want to show if this is okay. Let me show first and then I will tell. That is the reason. Okay, let me. Hmm. I mean, if I can show this, this is proved. Why this is proved? So I am writing rho x again here. Rho x is, what was rho x? G compose fx minus g compose fa minus mu. So if this is 0, then we are done. Why? This thing g compose fx, what? It is, so the derivative corresponding to this is the linear map this, I mean this thing corresponding to this thing, is this first, consider the first two terms. Sorry. Consider the first two terms. So it is G-composite. So if the derivative, in the form of derivative, the linear map should be D of G compose F A, right? Because for Fx, I am getting the linear map as D of Fa or lambda, or we name this as A because we are evaluating at point A. So the corresponding linear map of the derivative is this. But what is this? But mu compose this thing. It is a linear map, but mu compose this thing. So it is a linear map again. Corresponds to what is corresponds to what is mu and what is lambda. So lambda was D of Fa. So what is mu compose lambda? Mu, by definition, if you remember, mu is DGFA compose lambda. What is lambda? Lambda I assumed as D of Fa. So this is some map and this is another map. But if I can show this is 0, then the linear transformation is unique. I have proved that if lambda and lambda dash are two linear transformations, then they must be same. So this and this are same. That is what we want to prove in the theorem. That is the statement. So if I can by some way do this or this are equal, then we are done. And the and such the and such. Are unique. That is the reason. So our task reduces to show this is 0. Fine. Now you understand? Again writing what is rho x. It is G compose Fx minus G compose Fa minus mu compose lambda x minus A. Fine. Now put the values. G compose Fx is G compose Fx. G compose Fa is G compose Fa. Now what is lambda here? Lambda of x minus A. So from there, 1 lambda of x minus Fx, that psi x minus Fx minus Fa. Mu of lambda. So it will be, yes, phi x minus Fx minus Fa. So it is x, one just a minute, Fx minus Fa minus phi x. It will be Fx minus Fa minus phi x. From 1. Now you know that mu is linear. Mu is a linear transformation. So mu will break. So that will break. So that means let me keep the two things equal. Sorry, at one place, and if this is another place. Okay. Reason mu is linear transformation. But if I keep them in another bracket, okay, let's do in the next line. But this thing is what? I am regrouping them. I am regrouping them. Okay. So I have already defined what is this. This is this thing. Sorry, sorry, extremely sorry. This is this thing, right? So if you take y equal to in particular fx and v I have defined is fa. So this is psi of fx. This is equals to psi operated on fx plus mu by x. Okay. This is okay. So see phi x rho x can be split into two functions. So if I can show this 2 by x minus a when limit extends to a, this and limit extends to a this by this, they individually are 0, then the sum is 0. So our goal will be established. So we need to prove first thing, how many equations are there? 5. So 6 and 7 will be there. Limit extends to a by psi of fx mod x minus a equal to 0. That is equation number 6. And limit x tends to a. Separately, I will prove that will be a bracket here mu phi x that I need to prove here. 7. The two things I will need to prove. The two things I will need to prove here. Okay. So is there any obtained result that I could utilize here? So these two things in the obtained in the sense of in the first lemma what we have discussed here. So is there anything? Yes, we can utilize this. Observe that. What was the lemma? Let me recall. If this is a linear transformation and H is any vector from Rm, then I can bound that thing. That means it is a ellipsis. Okay. we want to utilize this thing. Observe that observe that in that thing, mu is a linear operator. So if I apply these things on mu phi x, sorry, mu these things, this will give me some m into mod of phi x. Now for phi x it is established. So that means for mu it will be established yet. Okay, let me write. Now using the lemma, which lemma? The starting lemma. We have a number m, matlab m is a real number such that mu of phi x is its modulus value, is equals to m of modulus value or norm, but we can obviously work with modulus value because any two norms are equivalent. Right. That means what? Limit x tends to a. That that thing is less than equal to m limit x tends to a. That is that things by that things. Okay. Then by so we have done. So this is 0, right? This limit because by this result we have written this, right? Where? Yes, by 4. Then by equation equal to 0. Right there. Thus, limit x tends to a, mu of psi x by x minus a. This is 0. So this is proved. This part is done. I need to prove this, but we cannot have. But the problem is that we don't have any. I don't have any information whether this is linear map or not, or this type of above lemma holds or not. I have no information here, so I cannot use this case. But we have one thing here. What we have? We have this thing, psi of y. So this is a limit statement. Limit means, by definition of limit, if that goes to 0, this goes, if that goes to 0, then there exists for every epsilon greater than 0, there will be a suitable lambda such that this minus 0 is 0. This is 0, but because the limit is 0. So this modulus less than epsilon, whenever something, this will be less than lambda. Okay. This is definition of limits. This is our definition of limit. from question 5 and by the epsilon delta function of limit, we have every pre-assigned or every given epsilon greater than 0 such that this thing modulus of this thing, what was the thing? Psi of fx, y is fx, you can treat y as an fx, y as fx. So let me write it just directly, okay? Psi of fx less than epsilon into fx minus b, there exists delta such that with there is a positive delta such that this, okay, because our we are tending fx or y, whatever you are taking, that to be. So this term psi of fx by x fx minus b, that whole thing minus 0 tends, this is, I mean, less than epsilon. So this by the mod will be not effective because already they are positive. So this by this, so this by this will break down, and I am multiplying both sides by this. But also the limit is here, this thing, y minus b. I mean, y tends to b. So y you can treat it as fx for now, for instance. So I can, I will get this thing. Oh, sorry. That will be delta. Sorry. But again, b equal to fa. We assume, remember. So what are we finally getting? We are getting lambda is, now lambda is given, and we are getting fx minus fa less than lambda. So treat lambda as epsilon now. Okay. Lambda is epsilon and f is continuous because obviously differentiable functions are continuous. I will prove this. So there will be some delta dashed such that this such that this happens will imply, I mean, this x minus a less than this delta dash. There exists a delta dashed greater than 0 such that what the delta dash will satisfy, x minus a. But again, so delta dash will depend upon delta such that I mean, so these facts will, I mean, this happens. I mean, this is the limit definition, right? What is the limit definition? Definition of limit says, or continuity says, if is continuous at x is continuous at a, if for every positive epsilon every positive epsilon greater than 0, fx minus fa less than epsilon, there is a delta depending on epsilon such that x minus a less than delta. So we are applying same thing here. B is fa. So classical by classical definition. Okay. So there is delta. So there will be obviously will be a delta. I want to how to write it. So that is delta dash such that fx minus b less than delta when you have minus a delta dash. Fine. So hence, what is psi of fx? Psi of fx is this thing fx minus b. But fx minus b, how you can define? Is there any way? Yes. Fx minus b is this thing. So this is psi x minus this thing. Psi x minus psi x plus, I think it will be psi x plus. So from there I can write it as epsilon fx. What is inside modulus? It will be psi x plus lambda x minus. I think it is by 1. Right? One equation. Yes. Again by triangle inequality, it will be epsilon psi x. Modulus, obviously, modulus will be there. Plus epsilon. Now, lambda, for lambda, okay, so let me write it as epsilon of lambda minus this. But again, by the lemma, by the above lemma, which we discussed first, for lambda also, there exists m dashed such that, because lambda is also linear transformation, so apply the result on lambda instead of th, so write lambda applied on x minus a. So also I could bound the modulus with some x minus a such that this modulus is less than, thus what we are getting, now, therefore, now take the corresponding ratio, limit x tends to a. This will be split epsilon. If I take epsilon common, this is this will be plus m, I think, right? But does this goes to 0? So that is 0. So that is epsilon m. But I can choose epsilon according to m. I can obviously choose epsilon according to m because we can control epsilon, right? We now we have information about m. So for every epsilon that holds. So now control epsilon has so small that is that product becomes more smaller than that. The product becomes even smaller or some less than every infinitesimal thing. So then you can replace these things by epsilon dashed. So we are getting it is arbitrarily smaller. So this is 0. Okay. Or whenever as or choosing not, I mean, as epsilon is arbitrarily small. Because we have chosen already chosen we have an information about sorry, we have already chosen epsilon. So whenever we are choose an arbitrary small epsilon. So that is 0. Our theorem is proved. That was the final thing what we needed to prove here.